we have the function y equals r of x equals x plus 2 times x minus 4 over x minus 1. We want to graph this. So again, I urge you to write out what you're doing. Okay. Here's your numerator. You find the zeros of the numerator. This breaks into x plus 2 equals 0. X minus 4 equals 0. This is solved easily. You get x equals negative 2. And x equals 4. On your graph, if the numerator is 0, r of x equals 0, provided the denominator isn't also 0. If you divide 0 by anything but 0, you're going to get 0. So your x-intercepts are negative 2, 0, and 4, 0. Okay, so put the line for x equals 4 out here. Line for x equals 2 over here. And we'll put a mark here and a mark here to indicate that these are x-intercepts. We get the zeros of the denominator. So we're going to write out x minus 1 equals 0. X equals 1. And that's going to be a vertical intercept. Not a vertical intercept, I'm sorry. It's vertical asymptote. Use the wrong word. Also then, y-intercept occurs when x equals 0. So we get y equals 0 plus 2 times 0 minus 4 over 0 minus 1. Well, it's easy to work that out. That's just 8. So the y-intercept occurs on the line where y equals 8, and it occurs at the point where that line intersects the y-intercept. Again, you see that I've put the labels for the numbers away from the axes so that our graph doesn't end up going through our labels. That's optional, but that's just kind of what I'm going to do, and it's what I recommend. Okay, well, when you do these problems, you want to write this out. You might want to say, okay, we're trying to find the x-intercept that occurs when y equals 0 and so forth. But the zeros of the numerator will make it 0. So when you have a rational function, you just do this and then conclude that they're the x-intercepts. If you're not writing this out, Then when you get a more complicated problem, you're going to get confused and forget the structure of the solution. There's a reason we do all these things. And of course, you're used to this. I mean, you drew all these three lines, okay, and everything looked pretty good. And on a quiz, you don't really have necessarily time to write all this out, although it doesn't take long. When you're doing your homework, do that. Write out what you're doing so that when somebody throws a curve at you, you can deal with it. Okay. So we're going to get the zeros of the numerator and the zeros of the denominator. These are the things we focus on for a rational function. Now, I'm not telling you everything. Sometimes the zeros of the numerator, a zero of the numerator will match a zero of the denominator. Okay. Like if I had an x minus 1 up here as well as down here, you can't just cancel the thing out. And we call that a removable singularity. And you need to read your text a little bit and see what the videos say about that. I could talk about that, but I want to focus on the basic bones of the problem. So there are things I'm not telling you, which you need to pick up from open math by reading the text, by working the problems, by looking at their videos. Okay. Well, what are we going to do next? Well, we noticed that to look at the long run behavior. Now, the way I advocate looking at the long run behavior is to figure out what power function this thing acts like when you zoom out. And we talked about that last time, didn't we? Yeah, I thought so. Talked about that both in this class and in the pre-calculus class. And the last time I remember talking about was in the pre-calculus class, but if I recall correctly, I did talk about it here. Okay, the long run. First of all, we expand the numerator so we get a polynomial in its general form, okay? X plus 2 times x minus 4 is x times x plus 2 plus 2 times x minus 4. We still have our x minus 1 in the denominator. And then x times x plus 2 is x times x plus x times 2. And then here it's 2 times x. I really have to pay more attention. I should have written x times x minus 4, not x times x plus 2. I wrote the x minus 4 here. I was careless there. And we understand it's x times this plus 2 times this. And this is this, not what I'd written before. So it's x times negative 4 plus 2 times x plus 2 times negative 4. All that over x minus 1. Well, that comes out now easily x squared. And we have negative 4 times x and 2 times x. That's going to give us negative 2x. And then we have 2 times negative 4, which is minus 8 over x minus 1. Now, the degree of the numerator is 1 greater than the degree of the denominator. Open math tells you, and everybody tells you, but open math will reinforce this, so I'm not going to write it down. When the degree of the numerator is 1 greater than the degree of the denominator, then you do the long division. which you attempted to do, nobody got it right, okay? Because you're trying to divide it into this form. You can't really use long division if you have a factor of 4. Okay, if you'd have done it this way, where the numerator is in the standard form, the general form, whatever, the regular form of a polynomial, then x goes into x squared, x times, right? So x times x is x squared, and x times 2 is 2x. And we're just going to follow the division algorithm, which I hope you've practiced and was assigned. And we just write a little auxiliary sign up here to remind ourselves that we're subtracting. So we subtract 2x from both sides. Well, I mean, we do 2x minus 2x, we get negative 4x plus 8. And the negative x squared and the x give us 0, so we don't have to write that down. And then we say, okay, minus 4, as x goes into negative 4x 4 times. And we have negative 4x minus 8. Well, again, we're subtracting the second expression from the first. So where we have minuses, we're going to put pluses to remind ourselves that when we subtract a negative, we really got to add. So we get 16. So it would be then this plus 16 over x plus 2. Now, x minus 4, okay, when x gets really large, 16 over x plus 2 is going to approach 0. Because you're dividing by x, the bigger x gets, the smaller this quotient gets. The bigger x gets, the bigger your denominator, and it'll get huge compared to your numerator, which means it's going to be a very small fraction. So we don't worry too much about this, but we worry about the x minus 4. So y equals x minus 4 is an asymptote. We call it a slant asymptote because it's a linear function and it slants up or down. Okay. Now y equals x minus 4. Well, let's see. The y-intercept would be negative 4. So we got y equals 8 here and y equals negative 4 probably go about here. And that would be the y-intercept of this asymptote. And actually, I'm going to use a different color for the asymptote. Okay, so this is a point 0, negative 4, x is 0, y is negative 4. That's a point on the y-axis. If y equals 0, then x equals 4. So it just so happens that this asymptote passes through one of the zeros. And that doesn't have any particular significance. It doesn't happen very often. I didn't plan it that way. Okay. I didn't know what this quotient was going to come out. Okay, so what we know is that if we zoom out, I have a good place to draw that, but I'll insert it up here. If we zoom out from a long ways away, well, if we're far away, this distance from the origin is going to look really tiny, right? So the graph will practically pass through the origin, but this is viewed from a big distance where this whole picture here is inside a little dot up here. So I say you got your wiggles and your asymptotes in this little region that we're magnifying down here. So when you get out of this region, right there is the line that the graph has to approach. So the graph has to come up from wherever this line is. I'm going to draw it here. And it's going to come up through this line. It's going to go through this point here. It's going to approach a vertical asymptote. Then it's going to come down or up from the vertical asymptote. Maybe it comes down like this, goes through this point, turns around and comes back and comes out close to this line. But it can't do that because if it comes down like this, to get back, it has to go back through the x-axis, and it can't go through the x-axis. The only way y is 0 is if x is -2 or 4. So it can't do this. There's another reason it can't do that. But just from what we have on this graph, we can conclude that it does something like this. Comes up from this asymptote, goes through here, then kind of turns around and begins to approach this slanting asymptote. The other way we know that the thing acts like this is that it behaves as a reciprocal function. If x is close to 1, then x plus 2 times x minus 4 is close to -9. So it's like you got -9 over x minus 1. What's -9 over x minus 1? What's the graph of -9 over x minus 1? Well, it's just a vertically stretched graph reflected around the x-axis because of the negative and shifted 1 unit to the right. Now, you have to understand the transformation application to the toolkit functions. But if you understand that, then this tells you exactly what this function should be. I have room to write it, but I'll write it anyway. So write it here. That's an important idea that most people don't grasp because most people don't ever really learn how to use the transformations or learn what they tell you. I'm pretty well dedicated in my class. And of course, there are people here who aren't in my class. People are distant students who aren't in my class. In my class, we're going to really continue to emphasize the transformations of the toolkit functions to give you a deeper understanding of this graph. And it doesn't have a lot of practical use in most fields. This doesn't really come up, but the whole thinking process and the ability to understand how all this fits together teaches you a lot about how to think and how to break problems down. It's one of the main benefits of this course. Ran into a former student, had no idea he was a former student. And he's some years older. He's middle-aged now. And he's a food vendor. He's talking to some other people, and then he turned to me and said, I had your physics class 20 years ago. I took the physics, I took calculus, took all the stuff. I went to work for a chemical factory, a chemical plant. And all the time I was learning that stuff, I said, how am I ever going to use this? What good is it ever going to do me? He said, every day in that job, in which he kept for 8 years, he used every bit of it. Now, you don't know where you're going to end up. Right now, he's a food vendor. He's it does some really, really creative and good stuff. He's still using problem solving. Cooking is a big problem solving. I'm still trying to figure out how to make black beans taste good. I've got all kinds of problem solving skills, but that one is escaping me. I've had them in restaurants where they taste good. I don't know what they do. Probably add something that's going to kill me. But, okay, well, that's just an aside. So I comment, this is something that doesn't necessarily have a lot of practical use, although I could give you examples and will later on of how a function like this could be really relevant to something you might want to know. Okay. But right now, we're just going to learn the mechanics. The mechanics of this is, what did I do? I'll even put numbers in these things. Let's see, what do I have to write with? Number one, find the zeros of the numerator and do what you already know how to do. Okay. Number two, be a bad looking two. Let's see if I can improve it a little. Okay, you can kind of tell that's a two. Number two, zeros of the denominator. Okay. Number three, long run. Now, in this example, the degree of the numerator was 1 greater than the degree of the denominator. So long division gave us a straight line. It's going to be the asymptote. If I'd have had one more factor in the numerator, that wouldn't have worked. Okay. I think I want to keep that because I did a real bonehead thing in pre-calculus class last time, and I want to show people my mistake. Okay, actually, need to put number 4 down here. Where in the world did I put that choice? I guess that's it. Okay. Number 4. sketch the curve. Of course, as you get this information, you put that information on your graph. I'm going to look at another example. Now this time, we're not going to need to expand the denominator because the degree of the numerator is 1. There's just 1 power of x up there. The degree of the denominator would be 2. It would be like x squared. It's x squared plus 6x plus 5. Okay? You don't need to be able to multiply that quickly in your head, but using the distributive law, that's what you would get if you multiplied it. All right. So go ahead and do what you can. And I'm going to just write out a couple of reminders, and I want you to write them in, okay? I just write them over here where I might not need the space. Zeros are the numerator, zeros are the denominator, and the long run. Make sure we at least focus on those things. Well, here's our function. And we do zeros in the numerator, and everybody did this right. And a 0 in the numerator is going to give us an x-intercept. Let's say x equals 0, x equals 3. The x-intercept is 3, 0. So we can begin to construct a graph. Let's do that here. But x equals 3. Yeah, we can put it about here. Sure, the camera is picking that up. And we can put a mark here because we have this point. 3, 0 is a point on the graph. So we mark that. You know, that's going to be a point on the graph. Zero is the denominator. Simply write out the denominator, set it equal to 0. By the zero property of multiplication, we know that this splits into 2 equations, one with solution x equals -5, the other with solution x equals -1. Now, when the denominator is 0, as long as the numerator isn't 0, you're going to get a vertical asymptote. So we'll say x equals -5 is about here, and x equals -1 is about here. And these are going to be vertical asymptotes. Now, what else do we know? Well, I didn't list the y-intercept, and I should have. I could list the y-intercept at any point. The y-intercept x equals 0, so y equals 0 minus 3 over 0 plus 5 times 0 plus 1, which equals negative 3/5. That's probably going to be pretty close to the y-axis. So say y equals here. And here's our y-intercept. Now, if x is close to -1, then x minus 3 is close to -4, and x plus 1 is close to 0. I'm sorry, x plus 5 is close to 4. So it's like we've got -4 over 4, which is -1, which means that the graph at x, the graph in the vicinity of x equals -1 is going to be like the graph of -1 over x plus 1. Meaning the asymptote's going to come up from below, and we're going to come over here, and we're going to go through this point. And then where we go after that kind of depends on our asymptote. Okay. Okay, so on the other side of x equals -1, graph's going to have to come down from here. Okay. Now at x equals -5, x minus 3 is -8, x plus 1 is -4. Should be like the graph of 2 over x plus 5. Meaning that the asymptote here is going to be like this on this side and like this over here. So what's going to happen is going to come down from this asymptote, going to come down here and turn around, and it's going to come back up to this asymptote. It has to be that way, even if you don't understand what I just said about what the function is like near -5, you understand that the function has to go through these 2 points. It has to be asymptotic to this line. So it's going to go through these 2 points. It can't turn around and go back through the x-axis to approach the asymptote this way. It has to turn around and approach it this way. The other side of the asymptote you can see if x is between -5 and -1, for example, if x was -3, you get -6 over -2 times 2. It'd be negative over negative and a positive. Okay, it'd be positive. So at a point in between here, you could test and see whether this thing is up here or down here. At this point, without testing it, it might do this. or it might do this. It can't hit the x-axis. And it's got to be asymptotic to both of these lines. Okay? So it's positive between -5 and -1. So it's this rather than this. Okay? Now, the long run is a little trickier, but I'll say large values of x, this, that's just not deformed very well. It was like that. You think of zooming out, you think of large x. If x is big, imagine x is 1,000,000. Then you got 1,000,000 minus 3 over 1,000,000 plus 5 times 1,000,000 plus 1. That's just about the same as 1,000,000 over 1,000,000 times 1,000,000, right? Because 1,000,000 minus 3 is so close to 1,000,000, you might as well just round it to 1,000,000. Okay? So what I'm saying is this is approximately equal to x over x times x. X is very big. This is approximately equal to this, which equals 1 over x. Okay? So long run behavior so if you zoom out, it has this behavior, particularly as you well, this approaches 0 as x approaches plus infinity. You divide 1 by a big number, you get a really small number. Okay? This one approaches zero from below as x goes to negative infinity. It's just the way the reciprocal function acts. You can also reason it out. If x is a big negative number, then you have a big negative over a big negative times a big negative. That's three negatives, which makes it negative. And since you have the product of two of those numbers in the denominator, only that number itself in the numerator, it's going to approach zero, but it's going to approach zero through negative values. And you notice that the y values in this curve are all negative in this half of the curve. The y values in this half of the curve are all positive because if x is a big positive number, everything's positive. You're approaching zero, but you're approaching it through positive y values. So that's what it looks like. So the lesson is over here. After this thing goes through zero, the axis, okay, let's extend the axis a little bit. It might continue climbing for a little while, but then it's just going to level off and approach zero. It's going to join up with like your reciprocal function. Okay, I'm not even going to try to draw that. On this side, up here, keep coming up and keep coming up, but it's going to start leveling off near zero. Okay, I'll make a note here. Just going to say this thing rises just a little bit, then it falls towards zero. Whenever the denominator has a degree that's bigger than the numerator, it's going to approach zero as x approaches infinity or negative infinity. Only question is whether it approaches from above or below. If this is a 1 over x squared, then the graph would look like, well, reciprocal square graph looks like this. It would approach zero from above in both directions, or possibly that would be a negative multiple of the reciprocal square and approach from below. Okay? That would be the zoomed out behavior, and you'd have your wiggles and your asymptotes somewhere in there, close to zero. I'll erase it because it's not relevant to this graph. Okay. Let's just take the function we just graphed, I just covered up. X minus 3 over x plus 5 times x plus 1. Let's say we want to solve this equation. Okay. So I'm just going to ask if anybody wants to answer this. Now, the question I want to ask is, what's the first thing you're going to do with this equation? Okay. Now, I'm going to multiply both sides by the denominator. Somebody, a couple of people actually wanted to expand the denominator, but then they kind of got hung up on expanding the denominator. We got to expand this expression, but we'll do it after we multiply both sides so we can see more clearly how it works. So we multiply both sides by the denominator. And what do? That means we write x plus 5 times x plus 1. Since it's a fraction, we'll do that. We'll put a 1 denominator there so we know for sure what we're doing. We multiply that by x minus 3 over x plus 5 times x plus 1. And then we multiply x plus 5 times x plus 1 times 4. Now, it is valid to cancel this denominator with this numerator because they're both, when we multiply fractions, we're going to multiply both numerators and multiply both denominators. So x plus 5 would be a factor of the denominator, and it's a factor of the numerator. So you can get rid of it. Okay? X plus 1 is a factor of the denominator. X plus 1 is a factor of the numerator. You can get rid of it. I'm going to show again, though, why this is so. This is the same as x plus 5 times x plus 3 over x plus 5 times x plus 3 multiplied by x minus 3 over 1. Why is it the same? Well, if I multiply the numerators here, that's the same as if I multiply the numerators here. They're exactly the same. If I multiply the denominators here, I still get x plus 5 times x plus 3, right? If I multiply the denominators here, I get x plus 5 times, I said x plus 3. Okay, again, if I multiply what's that 3 doing there? It's a 1. How did my 1s become 3s? Whatever AI is running my brain, it's doing more of that than it should. My eye picks up a 3 here, and my brain just decides to write it down. I hallucinated that, just like AI hallucinates. Which is no excuse. I should control my hallucinations. Okay. Let's try again. If I multiply the numerators here, they're exactly the same, so they're going to give me exactly the same result. If I multiply the denominators here, I get the same thing as if I multiply the denominators here, because this is the same as this, and in each case, it's multiplied by 1. Okay? Now I know that this over this is 1. So this is just 1, so I don't even have to write it. So what I get is x minus 3 equals x plus 5 times x plus 1 times 4. Okay, to solve this, if you look ahead a little bit, you see I'm going to get an x squared and a bunch of other stuff out of this product, which means this is going to be a quadratic equation. So I'm going to need to expand it in order to use the quadratic formula, or perhaps to factor what I get. Unlikely that it'll factor because I didn't set it up that way. Just use random numbers. but maybe it'll factor. Okay. Now I'm putting an extra set of parentheses around x plus 5 times x plus 1 because I'm going to expand this product. I get x times x plus 1. X is here and is one term in something that multiplies x plus 1. So x is going to have to multiply the whole x plus 1. Similarly, 5 is here. So 5 has to multiply the x plus 1. I still have 4 out here. The 4 has nothing to do with expanding this, but once it's expanded, we'll multiply it by 4. We have x minus 3 then equals x times x plus x times 1 plus 5 times x plus 5 times 1, and that's multiplied by 4. And unless you're very experienced and very reliable in your ability to correctly expand these things, don't shortcut this step. X times x, there. X times 1, there. Reinforce what you're doing with the distributive law. Now I can multiply x by x to get x squared, x by 1 to get just x. 5 times x is 5x. 5 times 1 is 5. We're not quite done. We can add the x and the 5x. That gives us 6x. Oh, that's multiplied by 4. And finally, I don't know if that's going to show up. I swear the camera is a bizarre thing. It keeps changing. And it's not the camera. I don't know if it's the camera, the tripod, or what. And now it isn't. Another line there, so we need to have room to write it. Okay. So we have x minus 3. We've multiplied 4 by every one of these terms. We're going to get 4x squared. 4 times 6x, 4 times 6 is 24. 4 times 5 is 20. Okay, well, we've got to continue up here. We get x minus 3 then. Just to copy it down is 4x squared plus 24x plus 20. So we put this in a general form and use the quadratic formula. Checking the time, we've got 6 minutes. Well, what we do is we subtract x minus 3 from both sides. And I'm going to do it like this. Let's write the whole thing out again. And you want to do this. You want to subtract x minus 3 from both sides. So you get 0 over here. Because the general form has a quadratic expression equal to 0. You have to have equal 0 before you can use the quadratic formula. So that gives us 4x squared plus 24x plus 20 minus the quantity x minus 3. Negative of x minus 3 is minus x minus negative 3, which is minus x plus 3. Now I'm going to switch sides just to put this in the standard way you want to look at it. I've got 24x minus x. Well, that's going to be 23x. And then I got plus 20 and plus 3. Well, that's plus 23. Now that's what this side simplifies to. And of course, this side has always been 0. So I just flip the two sides and we get this expression. So x, then by the quadratic formula, is negative 23 plus or minus the square root of 23 squared minus 4 times 4 times 23 all over 2 times 4, which is negative 23 plus or minus, doggone, you're going to make me do that in my head. I think that's 529, and that'll be minus 16 times 23, which is 368. I think 529 minus 368, 163. That's probably wrong. It's not too far off. And the square root of 163 is about 12.8. I'm not sure I like that. But I guess I like it. Okay, so that comes out to about negative 4.5 or negative 1.5. Now, that's not real close, but it's probably within a couple of tenths if I've done everything right. Okay? So the quadratic formula is just automatic. You just do the arithmetic and use a calculator if you need to, and you easily get a solution. Let's just test that against the graph. If negative 3/5 is here, where's 4? What we're trying to do is figure out where y equals 4, right? Well, 1 would be about here. So 1 positive 1, 2, 3, 4, be up about here. This is the line y equals 4. Right here is where we intersect the line. And we come down here and estimate x. We estimate x. Well, if this is -1, this is -5, here would be -3, here would be -4, here would be -2. It looks an awful lot like about -4.5 and -1.5. Okay. And that's exactly what I got. Not exactly, because I didn't do it exactly. If you run it through the quadratic formula, you'll find that it's a little different than 4.5 and 1.5. But the obvious estimates there, unless you made a very careful graph, would almost certainly be like 4.5, but -4.5, -1.5. The point being then that by doing this process, we get solutions. And this says that y equals 4. Of course, this is y. That y equals 4 when x is one of these numbers. We go back to the graph, figure out about where y equals 4 ought to be, about here, and we get estimates that are almost perfectly consistent with our algebraic solution. Okay. Okay, well, hopefully that's worth seeing.